Alright, so in this example, we have an AC generator connected in series to a resistor, an inductor, and a capacitor, right? If you've watched the previous video on a series RLC circuit, you will know where these equations and expressions come from, okay? So let's see. To start, we have the battery, right, or the generator, and then like normal, you have a resistor, inductor, and a capacitor. Okay. So actually, let me just go ahead and write the values up there. So the resistor I have as 425 ohms. The inductor is 1.25 henries. And the capacitor is 3.5 microfarads. All right. And the EMF, I guess, is 150 volts. Okay. So there are a couple parts, right? In fact, there are quite a few parts. However, each of them is not very involved, right? If you know the equations, they're fairly straightforward. The reactance in part A for the inductor and the reactance for the capacitor, as well as the total impedance. Well, the reactance, let's just put part A, it doesn't matter. I have plenty of slides. That's the beauty of technology. The reactance L, right, chi sub L, is equal to omega D times L. So note here, it tells us that the driving frequency, F, not omega, the frequency is 60 hertz, okay, and that's important, right? Otherwise, we'd be off by a factor of 2 pi. So the driving angular frequency is what we have to use in our equations. So remember the relationship between frequency and omega, right? Omega equals 2 pi f, right? The units for omega are radians per second, and, well, 2 pi is in radians. The units for f is in inverse seconds. So there you go. All right, so we have 2 pi times our 60 hertz times the inductance of 1.25. Okay, fairly straightforward. This should give us a value of 471. And the units, just like resistance, a reactance is in units of ohms. Right? It's a type of impedance, if you will. And chi sub c, that had the expression of 1 over omega times c. Well, let's see, 1 divided by our 2 pi times 60, and then the capacitance, 3.5 times 10 to the minus 6. And this should give us a value of, let's see, yep, 758. Right? And if we know both of these and the resistance, we can get the total value for the, well, the total what's that? The total, I don't want to say resistance. It's the total amount that the circuit tries to impede the flow of current. That's why it's known as impedance. Right? Z, it's a funky Z or script Z, or you can just write capital Z. Doesn't matter. That had the value of R, right? R squared plus, what is it, 1 over, let's do it this way, 1 over omega L minus 1 over omega C. And that was squared. And this whole thing has to be square rooted, right? Remember that. I did make a mistake in the previous video. I said everything inside the square root was the impedance. It's actually including the square root, right? Because the form has to be current is some voltage, right, the EMF, divided by a impedance, right, a units in ohms, and that has to be Z. So that includes the square root. So this gives us the resistance of 425 squared plus all those numbers. Well, we just found the various reactances. So 471 minus 758 quantity squared square root. All that should give us a value for the total impedance of 513 ohms. Okay. Again, remember, total impedance includes everything in the square root as well as the square root itself. All right, well, part B. Part B was the maximum current. Well, what I just wrote down, the current as a function of time is equal to the EMF as a function of time over the impedance. Well, remember the form of the EMF. It varies sinusoidally, so the maximum amount is, well, that coefficient. In other words, we're just worried about E naught right there, which is the voltage stated by the generator, or the stated voltage of the generator. So in that case, it's 150. For this part, we don't actually need to worry about the sine term. So just the max is E naught over Z, which is 150 over that 513. All right, and this should give us a value of 0.292. And the units current always are amps. The SI units, I should say, I guess. All right, next part C. What's the phi? What's the phase angle, right? And this is, remember, the phase angle in between the EMF for the circuit, right? The driving EMF and the current through the circuit. So we can find the EMF by using this relationship for tangent. Tangent was, phi. Tangent was basically the total reactance. So let's do it like this. Plus, whoops. Wait, did I do that right? That was that. There we go. Divided by the resistance. There we go. That is our total tangent of phi. Okay. And so we found both of those. Chi L was, in part A, 471. And chi C was our, I can't remember, 758? Yes. All over the resistance of 425, right? And I'm not taking the inverse tangent, but we should. Inverse tan of all that. That's a terrible way to write it. Tell you what, let me just take this, cut it down there. Such a cool feature. So now phi equals inverse tangent of that. There we go. And so phi should be about negative 34 degrees. There we go. That's the angle in between the EMF for the circuit, right, the driving EMF, and the current around the circuit at any given time. So the next part, part D, we want to find the maximum voltage across each component R, L, and C. Well, let's do I max for the resistor, right? V equals IR. So, wait, we want to find I max? No, V max. Sorry. V max for the resistor. There we go. Which means we need the maximum current, right? And so using Ohm's law, this is just V equals IR. We found the maximum current before, so that's 0.292 times the resistance. And this gives us a value of 124 volts. Same thing for, let's do the inductor next. Remember, for the inductor, we cannot use, well, resistance, right? It has to be the reactance, the inductive reactance. So the maximum current is the same. Now the inductive reactance chi L was 471. And so this should give us a value of 138 volts. And similarly for the capacitor. Now it's chi C. So 0.292 times chi C of 758. And this should give us a value of 221. Okay. All right, so part D was fairly straightforward. Part E, the inductance L at that phase angle. Right? So let's say the phase was to somehow change. So let's go one more slide for part E. Using that relationship, we have chi L minus chi C over R, and we want to find L. Well, L is embedded in chi sub L. So we have to extract it. So now we can solve for L. We know C, right? C doesn't change in this part. R does not change. Omega didn't say anything about that changing. And now we have a new phi angle, right? So a new phi constant. So let's see, solve that equation for L. We have R tangent phi is this stuff. And then bringing chi C to the left side and dividing through by omega and switching sides because I am weird like that. We have R tan phi and I'm just gonna do it like that, and then that's actually squared on the bottom. Plug everything in and we should get 1.36 henries. So compared to our other phi angle, where was it? The inductance originally was 1.25. If we have now a positive 30 degrees, right? They're slightly closer together, right? In time, in phase, slightly closer than 34. Well, we have a slightly larger total inductance, right? But that's how you solve for each of these various values, right? Properties, phi, chi sub L, chi sub C, right? From a standard RLC circuit. All right, thanks for watching.